Okay, guys. So it looks like no one is really joining. However, I'm still going to present this, and we can still explain some stuff, and we all can get some benefits. So this will be recorded anyway, and it will be on YouTube for later. So I hope you can see the screen, right? Everybody, like, in fact, you guys, you can still see the screen, right? Yep. Okay, right there. So obviously, we are going to talk about DirtyPipe LB, which is the local escalation. And some stuff here will be like kind of weird because I am the host and I am the speaker very much. Yeah, that's how it looks. So since like I'm right now working alone, so like you guys will see some stuff popping up, and because I'm posting on social media and other stuff. And this is me trying to explain to you what's going on. So if stuff starts to be crazy, please, uh, just be easy on me. And this is very much me after I understood what's going on. So yeah, that's what will happen. So before I kind of go through the whole presentation and show you some stuff, I would just want to show you how the vulnerability works, so we can have some kind of context what's going on. So very much this is like my machine, and if you want to understand how to set up the lab, I already presented all of that in the analysis on vsociety. I will attach the article link as well. So basically I have here, the exploit compiled and it's ready, and in fact, if I like this, something like this, you'll see like I have ton of stuff. And like even I have multiple version of the same exploitation, and the reason of that is because each version compiled with different flags, which means that it allow me to do different kind of debugging, and also it allow me to they like for example do something like tracing and stuff like this. So the G version, which is the one that it really works. So it's very much really easy. You just have to pass the file that you wanna edit, or pretty much you wanna overwrite. I'll explain all of that how it works. And after that, you have to give an offset, yeah, which is obviously a number, and I will. It's like very much to be specific. It's an integer, and I will explain later why you're doing that, and also in the end, a command or something you want to be overwritten inside that file. So very much when you just like hit enter and it worked, and that's all what you can see. So right now, if we did something like sudo art test, and sorry, it's not really sudo art test, it's just su art test switch. Okay, that's a bummer. It should really switch immediately. User art test does not exist, or the user. Okay, so it looks like it's supposed to work. That's a very nice example to see right now what's happening. So let's go to etc password, for example, and see what's going on. So usually you should have this here, and you should have see like that root, and it's supposed to be replaced to our test, and also this has to be overwritten. So okay, I have pretty much restored this. Let's see what will happen. So let's just log in. Yes, sir. Then terminal. Okay, so we're already in the desktop. So if I did CVE and we want the G version, right, and I have to give it the bass, which is APC bass WD I1, and like why are giving this, are giving this specific word, I also will explain this. So I hope it worked right now. It's supposed to work, please. Okay, like it's really just don't want to work. I'm sure I didn't update this. Hmm. So this is supposed to be the vulnerable version, and I know that I didn't update this yet. So this is supposed to work because I tested it. Okay, let me just like recompile the whole code again.
Bruh.
Yeah, I know. So okay, basically I already have another exploitation here, but I really want to present this one for a very specific reason. So basically, if I went to CVE 2022, which is the 084, and after that I run the exploit one, it's supposed to work. Okay, it looks like this got updated. This shouldn't be happening. Okay, guys, you have to give me a 5 minute here to like I don't know, find another lab that's supposed to be vulnerable. Just give me a sec. Recording to continue this. Okay, so as you see, I have like our. In fact, I usually have more labs, but I don't have enough storage anymore. So let's start again. And once it's getting started, you have to basically get in really quick, and you have to hit shift for a while, right? So you can access the grub, and here you can choose which version of the kernel you have, and I have like multiple versions as you can see. So I will go to the vulnerable one, which is 598, the generic one, and right now let it just load. And right now when we run the exploitation again, it has to work. So okay, logging in. Okay, here we go. So right now, just to check, you can just go and check the etc passwd or the etc password, and we can see here it's changed. What's really interesting is not that the username is changed. Of, by the way, this is the root. So like what is interesting that this here got deleted, which usually you have here the X, which is represent the password, right? After that you have the ID and the GID, you know, the group and the user. So we don't have it. So right now, if I did our tests, I'm just root. It's like magnificent, like how that happened, right? And I'll explain how that happened in detail, showing you how that worked from inside the kernel itself, doing static analysis. It's kind of hard to do debugging right now or dynamic analysis because that would take like at least 3 hours. Like even in my article, in fact, I was doing debugging for the exploit itself, not for the kernel. So going back to my presentation here, let's see. So as you can see, first we are giving three stuff, right? Like we are giving the file path, the offset, and the data, which is basically what we wrote here. So next, what happens inside the exploitation, and I can show you the code right now. Let me just find it. Okay, so here we go. By the way, guys, if you need like to zoom the phone or something, just let me know. Unfortunately, I can't see as usual, and tell the speaker to zoom in, so you guys have to do that for me. So basically, I won't really go through this right now, but here we can see that there is multiple if statements and checks that basically checking the offset, they are checking the base size here. What else? Basically, are calculating very much, and we can see like there are multiple checks. So it checks like for example if the etc password it didn't open, so it will give you like open failed. You have like multiple checks, and if all the if what you ever you gave the exploit passed all the stuff, we will go to the next phase, which is writing and overwriting the. In fact, sorry, we have right now to write to the pipe and write to the buffer. So usually I will go through and explain to you first how it works, but I want you to be confused a little bit. So we have something called pipe, and we have pipe write, and we have pipe read, and we have something called a ring buffer. No worry, I'll explain all of that, but I just kind of want you to have some stuff to think about right now. So what happened is we have here the pipe, and basically it write to the buffer, to the ring buffer, right, or the buffer ring, and that fill it up, and after that it reads it. So basically they are draining the buffer. So whatever you are writing in, it's getting drained again, and this process led us to set a flag. It You can call it only merge, which is like kind of a shortcut. So after that, we go to something called splice, and basically splice is really not. It's kind of just the general name you can find inside the kernel called splice.c. But there's a function called do splice, which is doing the real work. The real work. So we have splice, and what splice does, it tells the pipe like, hey, I will set you a reference there in the buffer where you can go and start writing after it. So we can see here, very much here. Okay, you can see here the offset, and it says plus minus offset, and we already gave 1, which means right now it's 0. So the splice take that, it's 0, and basically this offset, it's the offset will refer to the character we have in the first line, right? So right now you have here the whole file, which is etc password, as you can see, and when it gets set inside the kernel, or like let's say when it gets processed, you have to think about it as an array, right? So whatever is at the beginning here, it's 0. So as you can see, it takes the R, which is the first, right, from root, and it's set it here inside the buffer ring and say like, hi, here is your reference, and you have to start right from after it, right? And that's why when we give a test, basically it starts override this part, and I will show you. So you have the data input, which is like this one, test, right? You have this column. After that you have root column. After that the X. After that another column. And right now you have our test, because the test override the O, So you have T, E override the O, we have E, and etc. etc. And right now we have here the other column we have already, like we added, and we override the X. So that's why we don't have any password anymore, which is fantastic. I have here like more a manual thing. I was very much calculating by myself, and you can see this also in the article. So like you can here right here is the offset 0 where we have nothing, and after that it goes and it's like basically the same R. It will just be the same because like there's nothing overwriting it. And we have the T, which is like the offset 1, and it's writing over the O, and it just continue, right? And here our column overwriting the X, which obviously deleting the password. And finally we are good. So yeah, right now you think like that's it. No, we have like a lot of things to talk about. So okay, let's check the social media here. So how the vulnerability really works? I mean, like this was like very much not very much general, right? I mean, come on. So basically, we have what happened is when the exploit really works, it starts as the following. We have first something called prepare pipe, right, which is a function, and that function calling the pipe inside the kernel. So what is pipe? Pipe is just an IBC, and usually what we know, like I think a lot of people are familiar with, this, right, which is what called anonymous pipe. So usually, like for example, you write cat whatever etc pass the LED and like I don't know, you pipe it to grab, right, to grab. So you pipe it to that one, or to I think it was grab, whatever, or to less, or like whatever you have, right? You pipe it there, and what happened is the IBC is basically connecting two processes. So whatever getting out from there, it's getting into this, and anything after that process. So this is pipe in general, but the more you go inside the kernel, the more you find, okay, there's a lot of different things. And basically, I will also show you right now the the pipe.c, which is basically the C code of the pipe inside the kernel. So let me just get you the link. It's supposed to be here somewhere. Let me find it. So guys, again, if you want me to zoom in, just let me know. So right now basically you can use bootlane, which is show you all the versions you have in the in the Linux kernel. You can very much do some tracing and follow, and basically like jumping from one function to another. So this is pipe.c by the way, and all of things starting from here, and you can see like this file is huge, and I had to read all of that. So this is how pipe.c really looks like from inside the kernel. I mean, like usually for you just use this one and like, hey, it's working. Nah, I mean, like you got a lot of stuff from inside, right? So when pipe.c work, or in fact when pipe works as an IBC inside the kernel, especially when you are using it as like as a function, you have something called read end and write end, which you can think about it as like you have the write, which is like the start, and you have the read, which is like kind of the other side of the how the pipe work. And basically, what happened is you have a part where you write, and you have a part when you read. Like you have like 2 points. So and that's why you will see here right now inside the exploit you have something defined called pipe 1, which is for writing, and you have also pipe 0 for reading, or maybe I mixed them up, I don't know, but like one for writing and for writing and one for reading, right? So how it happened is first we create that pipe using this one, but this really it will be, I mean, as you see, it's just a void function, and it will be really called inside the main after you you enter the stuff, it all gets processed, some checks, blah blah. You go here and hey, you just call the prepare pipe, and this one, which will create the pipe. Uh, I mean, in the comments says with all flags initialized with pipe buff flag can merge, which is this is one of the main reasons why we are having this trouble right now. But really, it's not like that because when you go inside prepare pipe, which we will go in a sec. I already just walk you through all of that and explain to you the code. You will see here that we have four loops, one for writing and one for reading. And if you remember what I said here, uh, okay, I very much lost the presentation. Yeah, okay, here it is. I think it was in 6. Yeah, okay, here it is. So if you remember what I said here, you have pipe right, which is filling the buffer ring, and you have pipe read, which is emptying it, right, or draining it. And you see that inside the comments. So basically, the writing will initialize these flags. Right now, like we like, okay, like why we have this flag? Well, when the developers really created this flag and they added, and we'll see it later inside the byte.c, you will see like there is a flag and we have some called bit flag, which representing the flag. They made it because they want to have more efficient pipe that as IBC that work inside the kernel, because this will allow you to merge multiple, let's say, data together, which obviously will make it more efficient and even faster. So when you get this full and like, hey, I have still a little bit, space, I can get some stuff inside it. So I say like, hey, okay, let's merge some more stuff so we can have the full buffer used and we have more efficiency. But as a hacker, I've used this. So uh, the pipe write will fill the buffer ring, right? Which will initialize the pipe buff flag can merge. This is like kind of the full name, which is very hard really. And that, as I said, will allow us to overwrite the data, right? Or you can override, you can say update, you can say like really just merge, but kind of the term it's make it mergeable, right? So after that, since we have the buffer it's right now full, we have to drain that. So right now I was thinking like when I was working this, why I have to fill this and drain it again? It just doesn't make sense, right? But what happened is because there is an issue inside the code that doesn't reset the flag or reinitialize it. Once it's already set, it doesn't set again, right? Like when I drain this or whatever I do, the flag will be there very much forever inside the or like on the buffering, or on the byte buffer. And that's why I drain it, because when it's drained, I already have the flag there. I can refill it with what I want of data, you know, add more data, and I just can re-update the data I want, which is very smart. So after I drain it, right now it's empty, and I will exactly show you how really draining is happening. I can show you the code, but I will go through that later. I'm right now just giving you more of, let's say, theoretical information, kind of making sense and connecting that what I already was presenting here. So after that, as I said before, the splice will come in work, and basically we have, as I said, just take a reference and set on the buffer here and say like, hi, here is where you have to start right from after it. So what happened is the splice calls something called do splice, and do splice really calls something called copy page to item. So the more you go in the kernel, you see like there is always nested functions. So like a function called another one, and it just go in and in. So that copy page to iter, it really calls something else called copy page to iter pipe, because I will show you that later. Copy page to iter, it very much has multiple stuff, and one of the stuff that it has, which is, if you're familiar with user space and kernel space, we have two memories, very much virtual memories, And sometimes the only way, like there are in fact two ways to make whatever on the kernel on the user land to, or user side pretty much, to read or to access the kernel land is by using one of the ways is to give it access, like you have to give the user land stuff uh, access to the kernel land, which is that happens through something called syscall. But the other way is to copy stuff from the kernel, like we have data inside the memory, say the virtual memory, right? But this is only for the kernel side or the kernel land, and we can copy stuff from there to the user land. And the way to do that, we use something called copy paste to user, I believe, or to iter or something like this. So inside the kernel, we have only big function called copy paste to iter, and from there you have more nested function, which is each one copy to a specific place, user, byte, etc., etc. We'll see that later inside the code. So from there, I mean, like once you really do this copy, you very much told the script or the code, like, hey, you just have to start writing from there. And as I said, that's how the R, we have the R, so like it says the R as as where it will start from after it, so it will not write anything there after, it just like overwrite all this stuff. So right now we have R test, and we have the X just deleted, and we can, and we can just do su R test, and we are in with nothing. But also what is interesting here, and you have to notice, is it just overwriting inside the buffer, and this is like basically the base cache, and the base cache is it's something inside the memory, and it's very much the same as the cache inside your browser. So usually when you are browsing some website, it's getting cached inside inside your browser. And why they are doing that? Because each time you have to jump to the the ISP, and if the ISP doesn't have that, whatever you are calling or requesting, it will jump to the DNS server, blah blah, all that stuff. But if you already have that cached in your browser, that means you can just call it in milliseconds. The same, basically the same concept inside the kernel. They said like, hey, if I have some file already opened before, and it's already cached inside the, I can like put it in a base cache, which is like I said in the memory. That means when I want to call it again, I just don't have to go and call it from inside the disk and load it and open it, and it just, because like all of stuff happen, especially the more you dig in inside the kernel, you will see that more stuff really that there's out of write and read is happening, and I believe reading more than writing. But that means if I have to code each time from the disk, this will it'd be like just hard on the browser, on the on the CPU, on the processor, right? It'd be like just really slow, not really efficient enough. So if we already have it in the page there, I can just like code like that. And this is where it's becoming interesting, because since you are just overwriting it inside that page, that means wherever that page got cleaned, and how the page gets cleaned, it's very much the same inside your browser. Every time you make an update, or every time like you reboot your device, or like in my case the virtual machine, or I don't know, or like you are log out and log in again, there's multiple stuff that happen that can clean that that part inside the memory or that cache itself. So each time gets cleaned, you lose this escalation, escalation. You don't have that R test user anymore. You will just get back to the root, because when you are calling it again, like it got cleaned, you are calling the ATC file again. It will just like, we didn't edit anything on the disk, so it's just the same as it was, which is very nice thing to know about. And here's just the cat. So it's very nice thing to know about, because that means if you are a pen tester, a hacker, whatever, you need a persistent there, to hold your access. So in my article, I really go through what happens when you try to open a file, which will, I believe, will give you a lot of insight of what's really happening there. And let me get my article here so I can show you what I'm talking about. Pipe. If I switch it, okay, no, it's already open. Okay, it's opening. Then,
These bulbs need to be cleaned.
yes, sir, yes, sir. Otherwise, like auto escalation happening. And thanks, bro, for joining. It's really hard, kind of, to present this while you are alone. So this is my article. By the way, guys, we already have like a whole video, presenting the whole thing as animation. So the more that you go in, this is a very long one. So the more you go in, yeah, this is where I was just kind of simply explaining how what happened when you open a file, which is like very interesting. It's very similar. However, there are some differences, but this will give you a very much a good insight to what may happen, right? So as I already explained here, I'm not like just go through all of it. Like what happened is when you want to open something, which is by the way, let me see here. I remember they got the same open. Yeah, like as you see here, it's open. Like you have the same open function and getting a system call, and it opened the file, right? And here you give it the path and you give it like what is the permission, and here O are the only, which means read only. And by the way, all that stuff you will see already defined inside either the code kernel or inside the documentation. So usually they will call this, and that will call something called FD, which is a shortcut to file descriptor. And once it's called, the file descriptor is just an integer, and it's basically a number that's referring to a specific file. And like this is a simple illustration to what happens. So like you call this file descriptor, and that will be inside the file table, and you can see here like what you wanted, read, write, blah blah blah. And you have here the inode tail, which is, as you see, you have the path. In our case, like we got the etc path wd, which is the password. Also, we will have the file metadata, which is, for example, if you are using XF tool with etc path, you can see like some metadata information. So the more you dig in, really you'll find more stuff. I want to really go through the memory pages and how that getting handled and how it's managed, because I mean the photo itself is really enough to tell you how much that can we really dig deep and go details, and I don't think we have enough time. So after that we have the page cache, which is the cache which is pretty much what really interesting for us. And I here I very much explain what I explained already. We have some called having is called memory mapping, and after that we have the two ways of how you can access the data, either copying the data to user space, and that having user, as I said already, a function called copy to user, or you can use direct user land access, which basically giving access to the giving the file data in the kernel will provide user land access to that. Yeah, exactly. So basically, you're giving the user land access through the system calls, which can be really dangerous. Like, be, I mean, if you made any mistake while you are programming this, while you are developing this, and there is a way to control this syscall or like inject anything or like user after free or whatever, I have access right now to the kernel land, which means I can be the root. So this is very interesting thing also to look out for, either when you are hunting or when you are developing. So how they do that usually through read syscall or something called mmap, which is I believe a shortcut for memory mapping file IO. So yeah, I go here for some Bible stuff, and this is like very much where it's really getting interesting right now. So we already have here the, which one is this? I think this is the pipe. No, okay. So this is right now the exploit, right? The exploit code, and like why I'm starting here from the prepare byte, because like this is like kind of the main thing. So obviously what happened is it will start with pipe b, which is the function that it called from the from the system to call the pipe. And as you can see here, it's like creating a new pipe, and there is two file descriptor. It's like the p0 and b1. And as I said already, one will be for writing and will be for reading. So after that, it go and call something called size of, which is like this is the size of the buffer. And no, wait. So before it goes to there, it will call something called fcntl, which is, as you can see, it's already defined inside the documentation of the of Linux. And the fcntl, as you can see here, it performs the operation, which is like take an optional third argument, whether like little, okay. So take the file descriptor, which is like b1, the writing end of the pipe, and we can see that here. As you see, it's like b1, right? And after that we have something called v get pipe size, what is the size stored in the variable pipe size. So here we are checking the pipe size. Yeah, like you can't talk to the mic. And we go in, and after that where the writing really start. We go in, after that we have the reading. So I already explained this, I don't really need to go through it again. Very much when you read mine, like I'm really explaining each line, so I think explaining each line right now it will be very kind of boring maybe. One of the points that I was really confused, that generic, some kind of generic ring buffer, and the ring buffer, as I already showed you in the presentation, is like just literally a ring, right? So the ring buffer usually it has 2 points, the reading and the writing as well. So like you write from a place, basically you are entering a data and you're reading from the other one. But there is 2 modes for that. You have something called producer and consumer, which is the writing and the reading, and you have something called override. So there's also, it's all defined inside the documentation. I'm not really, I'm not a genius guy who read the whole code and and got to know what really happening. Nah, like I just go and read the documentation. So in the producer consumer mode, basically the producer is going to fill up the buffer, right? Before the consumer could free up anything, the producer will stop writing to the buffer. This will lose most recent events. So the overwrite mode, what will happen is it will lose the oldest event, because it will, like if you have 2 points, right, it will start writing from here, which will overwrite what is the oldest thing, which is very interesting. So I was like really lost here, because basically the 2 modes can work with this vulnerability, and but each one has a different scenario. So here is the main function right now. We can see in this in the exploitation, and basically the first part, as I already said, just like getting all the the data you are offering. I will check all of that stuff, and after that it will call the prepare pipe, which as we already said, like it will just initiate the pipe, create the pipe, and do the fill up, and after that the draining. Going right now to the splice, and the more you go down here, I'm really going through everything, like literally. So you can see all the syscall that we're using. You can see also splice, or it's already defined inside the documentation. They're explaining what it does. Uh, well, when I was researching this, there is kind of a debate about what splice exactly does. But when I was reading the code, and like the more I dig in, I found out that the splice literally can do multiple stuff based on the mood and what it's interacting with, which also was very interesting. Like, I believe it's worth researching. So in our case, as I said, it's like we really just set a reference, and from there the pipe will know where to write. So, and you can see, like guys here, like basically all the stuff from inside the documentation. So finally writing that to the base cache, the program then writes the new data, which is like data here. It's the variable which hold our data into the pipe. do the presence of the bybuff flag can merge. So flag in the buffer, the right operation, right the data. So like very much here, I'm really explaining again what happens when how we are explaining the buff flag and like what it does. And here what I already showed you guys. Here me being shocked because like when I understood this, for me just like magnificent, right? So we can right now dive inside the kernel. I'm not sure if you guys think that this is a good idea because that would take really a lot of time and a lot of me talking. So one of the stuff I really like about this that I can't search anything. So here, for example, when you search for
Yeah, I think such a big.
sorry, come again.
I think it's going to be a great idea.
Yeah, okay. So I will continue. Like we'll have a long night right now. So we have the pipe flag, and when you search it, you can see it's defined and referenced in multiple spaces or places, and you can see like it's in the pipe C and also it's in splice.c. And also you will see it here defined in the header, which is number 11, and you can see it here it's defined, and you can see it's can merge buffers as we already said. And here is what called bit flag, which is think about it as the number that's referring to what is to like it's basically referring to this flag. So I also already talking about bit flags here, and how it's like basically a programming technique to present multiple boolean value or multiple state into a single integer. So here you can see like the same exact photo that, or for the code. After that, we can go to the structure, which is supposed to be. Let me see. Yeah. So this is like the pipe buffer structure. I didn't really explain this exactly, but I think the more you read, the more it makes sense. So we can see here an pipe buffer. We can see the page, with the page containing the data for the pipe buffer, right? That what we were talking about. We'll need an offset. We will need a length, and this is one of the things I believe it was getting checked here. Operation associated with this buffer, what you're gonna do, and like basically you can refer to some called by buff operations, and you can see all the operations. I can just show you right now. I mean, I will not really explain this because it's a whole code, but we can still just check it for fun. By buff operations, yeah, and yeah, it's in a lot of places. Let's see, so let's check it here for example. So okay, by buff operation, and this say like it confirm verify that the data in the by buffer is there and blah blah. And you can see like there's two stuff. For example, you have confirm, you have release, you have try steal, you have get a reference to the by buffer. So this is all under the operation. Let's get back to here. So we saw the structure. So we are right now 40. Okay, so right now we are 44 minutes in recording. Let's just have another minute here. After that, have like a little break. So going to the pipe C, and very much here where we really go down inside pipe C. So guys, it just take 2 minutes. I had to get some water. I like really took a lot right now, and we will continue like in 2 minutes max.
Yep.
Nice, nice, nice. Okay, so I was talking about biopsy. So as I already said, in fact, I was opening biopsy. It's already open there. However, it's like huge, right? So I mean, I really recommend just go and read all of that. It's really fantastic. It will really help you to understand a lot of things. So let me just adjust the. Yeah, I think right now the. Okay, that's much better. Okay. So yeah, like there is a lot of functions, but like the more you read, really, it's the more makes sense how it works inside the kernel. However, I will be focusing in two very much two stuff here, two functions. It's the pipe right, and also we have the, where is that? Yeah, like we have pipe right here. I very much will go deep into this because I need to understand how. Yeah, like very much I only explained the pipe right, I believe, because I had to understand how it writes to the buffer, and that's what we are going to go through right now. So let me open pipe here on the side as well, which is also really interesting because, like, as you saw, the exploitation was really easy, right? It's like one easy command. You can even like get you can even get the exploitation compiled and ready. Like, you don't even need to do anything by yourself. Just like, hey, run it worked. Like you are root. But like when you start to analyze it, it's like, whoa, this is a rabbit hole. So what I'm gonna do right now, I will just try to find by bright. It's supposed to be like this. Yep, here it is. In fact, in the debugging here, I was presenting two pipes. One is called pipe test debug, which is basically I'm all like in the exploitation. I removed everything. I'm just using the prepare pipe because I need to debug that and understand more in depth what's going on. And I was only debugging this code instead of debugging the kernel itself because I believe like the already this article is huge, so it's like over 40. I think around 40 pages. So like it's really big, right? So debugging the code itself was very much enough, and after that I was redebugging the full exploit. However, I didn't really upload the files yet, but you kind of understand right now where is really the more important part. And I believe like if someone like really want to have more fun, can go even more in depth and go more like around what is by like not only by bright by breed, also go about the read and the write syscalls, and go also inside the splice.c itself and go more in more explanation, which we will do that right now a little bit, but obviously I cannot really dive a lot because as you see here, it's uh, 1431, which is huge. So we have first here. Okay, what is by bright? Okay, so as you can see here, but I know. Okay, maybe I'm writing. Okay, yeah. So we have struct, and we have these two structures. By the way, the IO of iter itself, this is like a huge another thing, and this is like it's kind of a feature for, I believe, the file system. I'm not really sure, but it's a feature that got deployed not that old, and it got basically deployed everywhere. Like as you can see here, it's IOV in everywhere, and also you will see this involved with other exploitations. So I would love to explain this, but obviously not now. But the more you also understand this, you will be able to understand other exploitations, which is great. So go back to here. So first we have just initialization and setup, as you can see. After that we have extract the pipe, inode info structure, which contain information about the pipe. And if we did this, like flip private data, I'm not sure if you can see anything right now. Maybe. Oh, okay. So basically, this is like variable. It will be like initiated everywhere. So like, we will not really be able right now to see a lot. So okay. Uh, define some variables. After that, we have some checking happen, which is like basically this check the total length, if it's 0 or not. After that, we have some code lock lock the pipe. And by the way, the same locking mechanism I'm not sure if I can say mechanism, but you say the same feature in a lot of other spaces, and it's always for synchronization. You will see it also in Windows, I believe. So, but I definitely saw the same locking thing in multiple other places, not only in Pipe itself. So, and also, yeah, also I saw that in Java. I saw it in multiple like Apache places, Apache like software when I was analyzing that. So after that, we go like more in. We see if like checking if Pipe has any readers. After that, it starts merge small writes, which is like very much where that really start to be interesting, because here we have the head and we have the tail, and this is what we were talking about. We have like Pipe, a kind of very much you can start to have start and end. At least that's how I see it in my mind. And after that, I want like kind of to go in here because we have a right loop. Yeah, which is, let's go page, a look page, not this one. Uh, well, like we should have some way a for loop somewhere here, which is for writing. Let's see. Guys, you are really free to participate if you like. Wait, pipe readers send a signal, which is like, I believe this is for breaking it. Yeah, this is for breaking. Like if there is no readers, it sends some kind of sig pipe, which is, if I remember this signal, it's also not sig pipe itself, but the signal kind of concept uses also when you like hit Control C, for example. So you go in, we have pipe full. All right. We have here the pipe buffer, head and mask. Okay. So I will very much read from here because to be honest I don't really exactly remember everything for that. But basically the mere writing loop attempts to write data into the BIOS buffer, which you can see this happening here, right? And until either all data is written or the BIOS becomes full, which is very interesting because you can see the BIOS buffer here where I opened that one. Yeah, like you can see it. I remember I was very much interested in it when it was, yeah, like here you can see it in pipe C. Also you can see it in splice C. Also you can see it defined here. I think this is the same structure we were already talking about. Oh wait, is this the same one? No, this is different. So like you can here literally see the whole structure for the buffer, which is amazing. So you can here see like it's a it's a it's a structure called page, and you have here after that inside integer, the offset and the length, and you can see the buff operation, and you can see the flag, and it's not quite private. I'm not sure what is private. Maybe it's the data. Or let's see here. User, recounter, writers, reader. So if you remember when I was explaining to you like how do you have readers and writers, I mean, like, yeah, we have the documentation, but also you can very much understand from here, and like you can kind of make sense and connect stuff together, which is I really like and I love, right? So we have the vibe C here. Okay, we have the right loop. So yeah, okay, so basically this is like the whole for here, and as you can see, as I explained before in the article, each iteration checks if the state of the vibe, if there are any readers, because like as you can see here, it will like basically go all the way to the end. I will start again from here. At any time there is any readers, it will send the signal, which basically will break it. Okay, and tries to allocate buffer space in the byte ring buffer, and then copies data from the user space. So if the byte becomes full and the writer is in non-blocking mode, it returns this, which is kind of a sign. A signal. And if the signal is pending, it returns this one. Otherwise, it waits for a space to become available. So this here, it kind of show you how it's not kind of it really show you how the whole pipe writing is happen, how it right inside the buffer, how it's keep checking the if it's full or not, giving the readers. Here we have the allocate page, so we can even see here allocate a slot in the ring in advance and attach an empty buffer. If we fault or otherwise fail to use it, either a reader will consume it or it will still be there for the next try. So I know that there are some code wake up somewhere here. So this is like the both two signals that we're talking about. Wait for buffer space to become available. This is like the both signals that we were talking about. So yeah, like we have here right now pipe unlock, which is wait, is this level one to wake the pipe up? We are going to release the pipe block and wait for more space. Okay, so we wake up any readers if necessary, and then after waiting, so like kind of the logic behind this is it send a signal for the readers like, hey, you can read. We need to recheck whether the pipe become empty while we drop the block. So I'm not sure if I explained the unlock here. Yeah, like you can see here, unlock and finalize, the pipe is unlocked and final wake up events are handled, so that you have kind of 5 time update, which is I believe this for synchronization. If data was successfully written, the 5 time that is updated. And we have in the end returned. Okay, so basically returns, it's right there. So basically, all this explanation is very much just a general one. The more you go in right now, you'll see that I'm explaining more in details the part where merge small writes happen. So, what do you think, guys? Do you think like we should go through this? I mean, I don't think like we have a lot of things right now here. Let's see. Uh, okay. So we already saw before the head, like vibe head, which is like this line gets the current head of the vibe, which obviously is the position where new data will be written next. You know, like as we said, like we have kind of two ends, one for write and one for read. And we have was empty, and I believe this for checking vibe empty head vibe to the tail. This function checks if the vibe is currently empty by comparing the head and the tail. It's comparing them here together, and it says was empty to true if the vibe is empty and false otherwise. Obviously, once it's true, it will like kind of rewrite if it's false. Maybe I'm not sure, but I think it will send a signal to the readers like to wake them up, like hey, you can come and read. And once it's once it's free, you can like the vibe can rewrite inside the buffer. So here like besides, I won't really go through all of that because what I'm more interested about right now is we have a place where I go inside the buffer. Yeah, when I go inside the flag. So where string flag happens. So I have this one here somewhere. You just can't find it right now. Okay, so here we can have it, right? So as you see here, it says if is bucket vectorized, and we have like basically two flags, right? We have something called by buff flag bucket, and we have something called by buff flag can merge, which is what is interesting for us. So we have these two here, but I know that is not set here. I know it's set somewhere else. Yeah, I went through this so much before. Like, oh, okay, okay. So I believe it was that part, right? Yeah, yeah. Here is where the setting flag happens, and basically this block will execute it if the last buffer can have more data. And this is kind of, as I said before, the idea behind behind the whole merging thing. And adding the new data to the current buffer will not exceed the buffer size, which is very important because like you can see it here is checking. And after that, the rest of the code, we have like this whole thing, which I believe is not like okay. No, in fact, I care about this. This is the cabbage from iter, and this line attempts to copy data from the iterator from into the buffer at previous computed offset. And I want to go through it right now. I just want to check where it was exactly. Maybe it was explained somewhere. Okay, it was. I'm not sure if it's here or not, but I will go through it. So basically, let's see. We have the cabbage from iter, right? We can see the offset, and we have see the from. Once we click on that, we have in the IO when IO and we have the IO that will be iter. Let's see where it was exactly. Because I did this like a very long time ago. Right now, I don't exactly remember everything. So we can see here the function. We have the page, the offset, the byte. Okay. Page copy scene. Okay. These are all like checks right now. I'm sure this was here somewhere. Okay, page from other info. Maybe under this one. So as you see, guys, like there's multiple kind of copying. But so basically, let me check this one first. This is defined in two places. This is as a function. Here there is a reference. So where we are. Okay, so like let's go through this one. Okay, skip. Here change enabled. Okay. And we're supposed to see somewhere. Okay, here it is. Carry base to iter pipe. And if I remember right, I explained something about this here. So I think this was in the beginning. So yeah, we have the pipe read, after we have the splice, and it calls something called do splice, and do splice calls something called copy base to iter, and after that copy base to iter will call copy base to iter pipe, which is this one. So like if you saw, guys, we basically jumped from copy base to iter, which is okay. I lost it again. No, from iter. Wait, there is from and there is to. So okay, so like basically we have it here, cabbage to iter pipe, and this one where it will very much start merging with the last one. This where we can see here really the merging is happening. And yeah, I mean like that kind of that symbol, it's not really that complicated. It's very much simple. Just functions calling each others, and at the end, the last one with some variables will know where to write, obviously based on what what data you provide for the exploitation, and it will just override the specific part that you want. And that's by the way, there's other exploits, and they do kind of this in a different way. Not the exploit, not kind of the vulnerability, because it's the same scenario, but instead of, for example, overwriting the root and removing the password, they are overwriting the password like only, and basically are changing the whole password and a new password. I don't really like that way. I like it the way and that, but that one you couldn't really provide that by yourself. So it was not like, it was kind of magic. You just like, hey, we are right now access root. But here it's kind of you have more interaction with what's going on, which I like. So you can see here also you have the tail, you have the ring size, you have the head, which is very much everything we explained already. You have some good pipe inode info. So yeah, I think that's kind of very much the end of it. Anyone have any questions? I'm not sure if you guys are even like I don't know giving up with what I'm talking about, or you are lost already. So guys, if you got no questions, I believe this is pretty much the end of this. Really, bro? You think it was great? Thanks, man.
Thank you very much.
You're welcome, bro. Yeah, let me just do something here. Yeah, I like this voice. V Genius number one on vsociety, bro. Do you have anything? Any comments? You know, like any questions? Yeah, I don't think he's here, or maybe he's muted or whatever. So yeah, guys, pretty much that's it. I believe this was like just.
Uh, yes, I'm here, but I was opening the mic,
Alright, bro.
I'm
Yeah.
using the phone. But yeah, it was good actually. And you know, I used it before. Just these pipes keep dirty.
You have the anonymous one. No, wait.
Yep.
Yeah, like you're saying like
No, I'm talking like the dirty pipe. It's close to the dirty cow. You know,
yeah, like
it's all pipes.
well, yeah, like basically, Dirty Cow is the ancestor of Dirty Pipe, and Dirty Cow is even more complicated than Dirty Pipe when you look at it. Like very much the exploitation, not exploitation. The vulnerability itself, it has a different scenario, but in Dirty Pipe, well, basically, when you kind of read in the previous versions of the kernel, when you read the code, you see like before the dirty web itself, it wasn't exactly possible until they defined stuff like the the merge flag, and they defined like I think the splice. So it's kind of more chained, but in the way I'm explaining it, I'm kind of trying to make it more of a flow. I think that will make it easier to understand. But yeah, I mean, like even this is not like really that complicated. There's some stuff that are extremely complicated, comparing to this one.
Okay, keep your Linux pipes clean.
Yeah, bro. Yeah, like, well, there is no really no batch for this. You have just to upgrade the whole kernel. Like, you cannot batch this one. I mean,
Yeah,
basically, you can
I
just
saw
do.
this, and I understand it from the stream and the analysis actually.
Yes, sir. So, guys, I think
Here
this
we
is,
are.
yeah, this is the end of this. And unfortunately, we couldn't have all people because, a lot of issues happen in the network. But yeah, thank you so much for the support. And see you in the next stream, I believe. Maybe we'll have you, Genius, in the next stream. Talking about some, maybe, I don't know, maybe the Win32, the escalation Windows. So, yeah, guys, have a nice night and peace out.